shall study them one by one. First of all, the nature of the living group. What means by living group? If you remember that this terminology, this group which is leaving this substrate is called living group, and anything which is approaching this is commonly called nucleophile because this is electron rich. So two terminology we have introduced already. So living group, nature of that. What kind of group is it? Either this is having a charge and that charge stabilize. If it make a stabilized charge, then the ion shall be which is in ion generated, so it shall be stable. If it is more stable, so it shall be very easily broken. Otherwise, this shall be not easily broken. Right. Now look at here. If we are having a X group attached to this carbon, if you remember X group, which is halogen, I have presented here for an example, fluorine, chlorine, bromine, and iodine. So these groups are all halogen have electronegativity higher than carbon. So in all cases, the carbon shall be partial electron deficient, delta positive, and halogen shall be delta negative. They shall be having a high electron density towards them. So this carbon shall be electron deficient and this X shall be electron rich. So if it is going to, this reaction is done in aqueous medium, let's say. So if we have a fluoride ion from gas converts to aqueous, right? Let's say we are doing this reaction in gas phase and this iodine generates in gas phase, fluoride ion, bromide ion, and then they are added to water. So whenever ion from gas phase adds in water, it forms what energy it releases, which is called solvation energy. So you would have come across this in physical chemistry about the solvation energy. Mean you have also come across solvolysis. So let's say why sodium chloride dissolve in water, because when sodium chloride dissolve in water, it has a high dielectric constant. It produce sodium ion and chloride, and sodium ions are being trapped with water, oxygen of the water. So this is called solvolysis. Similarly, chloride ion carries negative charge. It is hydrogen bonded with the hydrogen of the water molecule. So this is how the chloride and chloride ion and sodium ion, anion and cation, both are being stabilized by solvent. This is what we call solvolysis. And during the process of solvation, some energy is liberated when an ion from gas phase is converted or solvolized by a solvent. So because we are using water, so this is called aqua or solvolysis by water. So anyhow, if it is a fluoride ion, it liberates minus 117 kilocalorie per mole. If it is chloride ion, it produces minus 85. If it is bromide, it produces minus 78. If it is iodide, it is minus 68 kilocalorie energy releases, right? So if it is releasing such amount of energy, the iodide ion is the most stable. Theoretically, if we look at, if it is fluorine, it is the most polar bond. So most polar bond, it can easily break up. Fluoride ion can break up, but look at here. When it goes to aqueous form, it liberates a very high amount of energy, which makes it unstable. So fluoride ions is very rare. It shall undergo the loss of this, right? So the best minimum energy released during solvation energy is basically produced by iodide ion. So if it is iodide, it is the best living group among halogens, right? So in a period, if we sorry, in a group, if we are defining, if we are moving down the group, the more living group it becomes better living group to live, rather upper one. Let's say if nitrogen is living in the form of NH2, so it is very rare. But if it is a phosphorus compounds, then they can live more easily, right? So this is the trend that we set. So oxygen, OH leave, very poor. We shall not see anywhere OH leaves if we have alcohols. But if it is a sulfur with some oxygen electron deficient, it can easily leave. So anyhow, this is one of the factors. If we are moving down the group, then the leaving group leaveness increases. And let's see further nature of the living group I am defining. Just focus on oxygen living group. If we have OH present, alcoholic present, attached with what I have presented, this X group is suppose it is OH. So if OH leaves, it shall be in the form of OH negative, very poor, very rare chances. But if let's say this is acetatine O bonded with the acetatine, so it shall be likewise. If it is let's say sulfonic acid type moiety is attached, so it shall result O negative likewise. If let's say this is colorate, like this is colorate ClO4, this is attached with the same entity, so it is generating this. Now in all cases, if you notice, there is a negative charge on oxygen, mean oxygen is a living group. Oxygen is carrying a negative charge as a living group, no doubt. This is nothing surprising, but all of them are not having equal reaction rates. If it is colorate, it has a very high reaction rate. If it is sulfonic acid, it has a stronger, again, faster reaction rate, but less than colorate. With acetate, this is moderately good, but with OH, if it is alcoholic, very poor reaction rate, very poor, negligibly small. So how we can compare this? Let's see, if this is a OH, it is not stabilized. It is not stabilized. But if it is acetatine, you see it has two resonance forms. This oxygen delocalizes here. This oxygen takes electron pair. So we can draw two resonance forms with this. Look at sulfonate. Oxygen can donate this electron pair here, and this oxygen can take electron pair off. Or this oxygen donate electron pair, this oxygen can take. So we can draw three resonance forms for that. And look at here, if this oxygen donate electron pair here, this oxygen can date electron pair off, this can take off, this can take off. So there are four resonance forms possible with this. More resonance form, if you remember, you have come across in previous semester the rules of resonance. If more canonical forms are presented by a molecule, so it shall have more resonance energy. More resonance energy means more stabilization. So it means colorate is having four resonance form possible, having oxygen negative charge. Sulfonic acid having sulfonate having oxygen negatively charged as well, but three resonance form. Acetate having two resonance form. OH having no resonance form. So it is unstable in fact. It is having a poor stability. This is more stable and this is most stable among them. So we shall say colorate shall be the best living group among these four. Moderate shall be this one, and very poor or satisfactory you can say is this acetate, and very poor can be OH. So this is what I have presented in this nature of the living group. So which living group is the best living group among them? In case of colorate, we don't have any diversity. If oxygen bonded with colorate, so we don't have a diversity in this molecule. But we can have a diversity in this case. Let's say if this AR group or alkyl group attached to sulfur, if it varies, then we can have this difference. So a lot of different groups are being, we are having a good living group. Acetate, we cannot get that change. Or if we change the alkyl chain along with this, so alkyl chain is electron donating, it shall become a poor living group in that case. So anyhow, the only we can change this aryl group here to have a electron withdrawing groups present on this aromatic system, or we can have an inductive effect of this. So electron withdrawing. So we have sulfonic acid type. It means we are having this carbon bonded with oxygen. Oxygen is further bonded with this sulfonic acid, this one. This oxygen bonded with the carbon, then oxygen bonded with sulfonyl, and this aryl group or alkyl group, so whatsoever. So it has a diversity. We can introduce so many types of this. I have presented them two different groups. In one case, I have attached an aromatic group, which is benzene in this case, and at the para position we have X group. And in the other case, we are having sulfur directly attached to alkyl group, which have electron withdrawing nature. So let's say if this X is, in first case, I have presented, if this X is methyl, this is called paratoluene. So this is commonly called paratoluene because if you see this methyl group is at para position to this one. So this is paratoluene sulfonyl, right, or sulfonate, because this is an ester type, oxygen bonded with alkyl group. So this is carbonyl, oxygen bonded with alkyl. This is due to this difference. This is called sulfonate. If we have a hydrogen here, this shall be called sulfonic acid. All right. So this is called sulfonate. So what sulfonate? This is paratoluene sulfonate. This is paratoluene sulfonate, and this is abbreviated as OTS. This oxygen is O, all right, and this whole group which is present here, other than this oxygen, because this is bonded with carbon, this group is called tosyl, TS. TS. This group I am presenting in arrow. This group is called TS group, tosyl, right? And this bonded with oxygen. So this is called OTS group, including this oxygen. This is called tosylate. One is OTS is the abbreviation we give it to this, and this is when we are reading this. This is called tosyl group or tosylate because this is an ester type linkage. Second, if this X is bromine, it is parabromobenzene sulfonate, right? And this is this is called brosylate, right? And this is abbreviated as OBS. Looking at small s here. Oxygen capital, this is element. B stands for abbreviation bromine, and S for sulfonate. Bromosulfonate. This is definitely parabromobenzene sulfonate. So this is called brosylate. In fact, if this X is nitro group, right, it is also present at para. This is para nitrobenzene sulfonate. This is represented O in oxygen, N for nitro, and S for sulfonate. So this is called ONS, and this is commonly read as nosylate, right? So you see all of them are ending with ate, just like a nomenclature of the ester, and it is oxygen bonded with alkyl, right? Is it clear to everybody?
Yes, sir.
Hello, are you sleeping, everyone?
Sir.
No, sir.
All right. So this X group is very important. If we look at methyl is electron donating by inductive effect. In Wien, we can call this is a plus I group. If we look at bromine has three non-bonding electron pair. It donates this electron pair here in resonance, negative charge here. So this is increasing electronic density, but by resonance. So bromine is a, in other word, you can say this is a plus R group. This is electron donating by resonance. M is plus I. It is electron donating by inductive effect. Bromine is a electron donating by resonance. So it is plus R. Nitro group, if we look into, this is totally opposite. If you see, nitro group generates, you have seen in aromatic substitution, it generates a positive charge at ortho and para. So it is creating a positive charge here, which is making this electron deficient. So it shall, if this positive charge is here, it shall withdraw electronic density from sulfur. Sulfur shall withdraw from oxygen. Oxygen shall withdraw from this carbon. Even if withdrawing, so polarity is changed. So nitro group has a inductive effect is zero because it is opposite to this group. Zero inductive effect, but it has a minus R effect, mean electron withdrawing by resonance. So in that case, this is more reactive. So it shall make more polarization between this oxygen and carbon bond. Now let's see, rather this aryl group, if we are bonding here, simple methyl group, right? So this is called methyl sulfonate, or methane sulfonate is also called, but this is represented with MS, OMS, OMS, O for oxygen, and M for methyl, S for sulfonate, methyl sulfonate, right? This is commonly called mesylate, mesylate. Some people read this mesylate or mesylate, whatsoever you would prefer. If we replace this Y by CF3, mean in case of methyl, all hydrogen are replaced by fluorine. Fluorine or electron withdrawing by inductive effect. So this Y group methyl was electron donating. It was electron donating, but when it is CF3, no, it is electron withdrawing. So rather it is plus I, no, it became minus I. Now here it reverse. So when it is minus I3, fluorine withdrawing electronic density from carbon, carbon shall withdraw electronic density from sulfur, sulfur shall withdraw electronic density from oxygen, oxygen shall withdraw electronic density from carbon. So the bond polarization is increasing. We shall favor the leaving group to leave easily. Now look at here, we are having CH2, CF3. Now we have increased our group CH2 in between CF3. So it is causing a decrease in fact, this effect. CF3 is not directly attached. A carbon is in between. So the effect is decreased. So CF3 shall be more reactive and CH2 CF3 shall be less reactive. This is commonly called 2,2,2 trifluoroethane sulfonate. So this is represented with OTR. OTR TR stands for tracylate. Tracylate because trifluoro is there, but it is present on the ethane molecule. So anyhow, if we have a butyl group, all hydrogens of butyl group are replaced by fluorine. So this is called nonafluoro, nonafluorobutane sulfonate, and this is represented with ONF, ONF, and this is called nonaflage. You see triflate OTF, this is triflate, trifluoromethane, trifluoromethane, OTF. F is wherever this is standing for, in fact, fluoro. OTF means fluoro, but trifluoro means CF3. And this is ONF fluoro, but nonna, N stands for nonna, 9 fluorine, which is C4F9. So this is triflate, nonaflate. So nonaflate contains 9 fluorine, which is most electron withdrawing. So when it is most electron withdrawing, so it shall withdraw electronic density more here, and this oxygen carbon bond shall be most polarized. So on the basis of this electron withdrawing or making oxygen carbon bond polarized more. Number 7 called nonaflate. Nonaflate is the most electron withdrawing by inductive effect. Then it is not CH2 CF3, it is directly CF3. CF3 is more electron withdrawing, and then it is CH2 CF3. So the order shall be like this: 7 shall be most electron withdrawing, then 5, then 6, and then it is 3 nitro group present here, not methyl. Methyl is electron donating. Then it is 3 nitro. Afterwards nitro, we are having number 1, which is methyl. All right, so methyl is away from there, but in this case methyl is directly attached. So 2 is least one because this is electron donating. Bromine has 0 inductive effect, but to some extent this is increasing. So that's why this is the due to increase in electronic density, this is the in the end, right? So this is the order of polarity. or you can say polarity order. So 7-1, if it is a 7 group present sulfonate, 7 form, it shall be most electron withdrawing. Then it is 5, then 6, then 3, then 1, then 4, and least one shall be 2. So rather it withdraw electronic density, it is donating electronic density towards this. So this is something that I have presented the groups, leaving groups. If we are having a alcoholic group present, it doesn't leave at all. We cannot make this alcohol leaving in the form of OH impossible. All right. So how we make oxygen leave? We react alcohols. You have already come across in here. Let's say this alcohol was not a good leaving group. That's why we reacted with thionyl chloride, which results in this. So now it became a good leaving group. Or oxygen reacting with sulfonyl entities like this one. In this case, when we are reacting sulfonyl chloride, right? So it may be OTS chloride or TS chlorine, TSCl, not oxygen attached. Then this alcohol reacts with this carbon sulfur and this electron pair from chlorine. It takes that electron pair of oxygen, donate electron pair back. So we are having this oxygen bonded with sulfonyl. This is the reaction mechanism. Very simple carbonyl type addition is going on. Alcohol act as a nucleophile. Very similar I have presented here. Here we have sulfur bonded with one carbonyl. So one chlorine is leaving. So this oxygen is bonded here. This is very similar to this one. This one is very similar. So we have sulfur two double bonds with oxygen. One of them takes electron pair off. So oxygen, this nucleophile approaches the sulfur, and then this oxygen donate electron pair back, and one Cl leaves from the system. So we get this oxygen bonded with sulfur, and we are having Cl is lost. So sulfonyl chlorides are converted into sulfonates. If this X is methyl, it shall be OTS. If this group is bromine, it is OBS. If this X is nitro, it shall be ONS. And if this sulfonic acid is methane, is Y is methane, so this is OMS. If this Y is trifluoromethane, so it shall be OTF. Similarly, if it is nanofluoro, nonafluoro, or tracylate, etc., so we can have a variety of them we can synthesize. So once we have an alcohol molecule, alcohol can be made a good leaving group reacting with sulfonyl chlorides. So it shall form sulfonates. A variety of sulfonates shall make it a good leaving group, in fact. So a bad leaving group can be converted into a good leaving group. If we have a nitrogen suppose present, nitrogen is also not a good leaving group. So I have already presented. Let's say we have OH group present here. It is not a good leaving group. We cannot make it leaving. So it is not a leaving group. So if OH, then it can be reacted with sulfonyl chloride, a variety of them, then it shall become a good leaving group. So let's see if this is nitrogen. Nitrogen is not a good leaving group again, and H2 is not a good leaving group. How to make it a good leaving group? You remember, if primary amine is reacted with HNO2, nitrous acid, it results in the formation of diazonium. This diazonium is a very good leaving group because when it leaves, it forms nitrogen gas. So NH2 is converted into a good leaving group as in the form of diazonium. So that is a good technique. But if let's say this is sulfur SH, so it is also not a good leaving group. We convert sulfur into thioether, and then we oxidize sulfur with some oxidizing agent like MCTBA you have already come across, ozone, and many other oxidizing agents. So it oxidizes to sulfonyl entity, then it can become a good leaving group. So these are, whenever we are having a leaving group, if it is not a good leaving group, we can make it a good leaving group, right? And similarly, if a leaving group leave and it is resonance stabilized, it can leave very easily. So these are the factors which are associated to understand relevant to the leaving group. So whenever we are having, so if we have a substrate, in the substrate, if leaving group leave easily, the carbon bond with leaving group is polarized, and the leaving group which leaves is a resonance stabilized, then it can leave very easily. So it is a good leaving group, the Michel bond. Just hold on. All right, so this is the one of the factor we have come across, the nature of the living group. I shall discuss another one, because during substitution reaction, you have seen one we have a substrate, other we have a nucleophile. So we have seen in a substrate, living group nature is very important. And the structure of the nucleophile is also very important. Sorry, structure of substrate is also very important, that you shall see after next three mechanisms again. So anyhow, I shall cover another one, the nature of the nucleophiles. You have already come across in substitution reactions, sorry, addition reactions, about nucleophile, carbonyl addition, if you remember, soft nucleophile and hard nucleophile. So you have already come across these two kind of categories. But when we are talking about perspective to the uh, nucleophiles, you see in this case, iodide is the best ion, no doubt. So I have skipped over here. So first of all, it shall be iodide, then it shall be a thio S negative ion, and then SH ion, because here R group is electron donating. So it is making this negative charge more stabilized on sulfur. If it is hydrogen, hydrogen is neither electron donating nor electron withdrawing. So it is not going to affect to a larger extent. So that's why SH group negative is less nucleophilic than SR group, right? So similarly, NH2 negative, OH negative, they are better. Charged nucleophile are much better. Why? Because in these cases, when they carries a negative charge on them, they becomes more active. When they are negative, they have electrostatic forces of attraction towards electron deficient center. So this makes them closer to each other. And look at here, primary amine, they are not having a negative charge, so they are less comparing with NH2. This is charged, this is uncharged. Although presence of an alkyl group is increasing their density, but if it is NHR, NHR shall be better nucleophile than NH2. All right, negative charge. So this is just a comparison you have already come across with these two. Iodide shall be the number one. Similarly, proceeding OR mean phenoxidine. Phenoxidine shall be more stable than the alkoxidine, which is coming later in the end, which is more harder. Just compare here. We have O negative, O negative, O negative. These are the three. Alkoxide ion, but this is aromatic group attached, here alkyl group is attached. Here this O negative is resonance stabilized. Here this O negative is not resonance stabilized. This is the only reason. This is more stabilized by resonance, right? This is the reason it is more stable than this one. Similarly, ammonia, azine, chloride, water is a borderline case. This is the above this, they are stronger, soft nucleophile or good nucleophile. As we are moving down, now they are becoming harder. So they are not good nucleophiles, they are good bases. Chloride ion is a good base. If you remember, alkoxide ion is a good base. We use sodium ethoxide, sodium methoxide as the base. So they are good base, but not good nucleophiles. Similarly, NR2, it is not a good nucleophile due to steric factor, in fact. And similarly, R3 negative ion. Due to steric factor, it is not good nucleophile. keeping in mind. And chlorate, it is a good living group, but not a good nucleophile. All right. So this is clear. Just I'm going to clear this with one example. Let's say if we have a R3C, if this R is hydrogen, let's say this is methyl bromide, in other words, if we are reacting this with water or we are reacting with a base OH negative, sodium hydroxide, potassium hydroxide, here we have a negative charge on oxygen, here we have no negative charge on oxygen. So it does make a big difference towards reaction rate. Look at here, if rate constant is K1 for this, and if reaction rate is K2 for this, in this case both are resulting the same product, right? So in this case K1 is, and ratio to K2, this is 5,000 times faster. If we are reaction, we are doing this bromide, this is bromomethane, we are having reacting with hydroxyl ions. This reaction shall have a 5,000 time reaction rate if we are comparing it reaction methyl bromide adding in the water. It shall be very poor reaction. On the other hand, we have R3CBr, mean where this R is methyl, mean this is trimethyl bromo. This is a tertiary carbon, this is a methyl carbon. If we are reacting this with base, if we are reacting this with water, so K1 and K2, they are same. They are not making any difference. Why? Because if this is tertiary carbon, it follows SN1 mechanism. And if you have seen already SN1 mechanism, in SN1 mechanism, the very first step, the substrate reacts to form carbocation, then nucleophile reacts. And rate determining step, there is no nucleophile. So it doesn't depend upon the nature of the nucleophile. Whatsoever is the nucleophile, either nucleophile is charged or this is uncharged. It doesn't make any difference, because with respect to kinetic studies, SN1 reactions are zero order with respect to nucleophile. So this is the reason they are not going to react in that case. So they are having same rate. But in case of SN2 reaction, the presence of charge or uncharged does make a difference. The presence of charge or uncharged in SN1 mechanism make no difference at all. This is very important to remember. So this is a summary that I have highlighted about the one of the factor is the nucleophile, or the nucleophilicity of the nucleophile is important. More nucleophilicity it have, more stronger it shall be a nucleophile. All right. So two factors we have seen. The rest of the factor, the steric factor, polarity of the solvent, and SN1, SN2, Snene's concept, etc. So we shall discuss that in next week.